Well, I only demoted you. Oh, it says this conference is being recorded.
I guess I had that option. I just found it.
Oh, now, all right. Well, then that's fine. We'll go ahead and start. We're at, let's see. Today is, what is today? April 2nd, 2016. And as of this moment, we have 9 people. And we're hoping to get a few more, but we understand that 2 things. Number one, that we're not in the habit of having Saturday morning meetings as we used to do, and so a lot of people don't know about it. The email that I know about that went out recently by David went out 15 minutes ago at 8:45 my time in Central Standard Time. And so the other thing is I imagine that some people are struggling to get started, just to get in. Dennis Allen is here. Good to have you with us, Dennis. I don't think I've seen you here before. And a lot of people, including myself, are struggling to figure out how to use the new system. Somehow Jeff was able to get the recording started, and that was a surprise to me. Normally the host does, oh, I see a record button. It's up in the upper right. Now, how did I miss that before? Well, anyway, so we are recording, and I'm not going to turn it off and turn it on again because that would be confusing. And I probably couldn't figure out how to do it anyway. I'm still struggling to figure out how to use the chat. There's both a private chat, which you can have with any person, and then there's a public chat, and I don't know how to move to the public chat. So I'm just now chatting privately with Nick. I can, but maybe that's how it works. Maybe there is no longer a public chat. I'm just not sure. So if anybody figures that out, please let us know. The numbers are going up. I think we're up to about 11 or maybe 12 now. I'm not sure. So that's good. Because people are kind of coming in. I'm trying to uh, create a little bit of time here, just because I think people are still trying to get in. If you're like me, you're probably struggling to figure out the new system. So go ahead and press some buttons. If anybody wants to be promoted to presenter, I can do that. The protocol is if everyone can kind of turn their microphones off. So far, there's no feedback, and that's great. To avoid feedback, generally the headphones work pretty well. That just avoids with the feedback situation. What happens is the presenter or the person who's generating the feedback is the only person who doesn't know about it because the sound is coming to them. Then they're putting back their own sound, and it gets really bad. So the way to avoid that is to have a headset. If you're not presenting, it's not a big deal. Just turn your microphone off, everybody, please. There is some background noise right now. I don't know who it's coming from, so I am going to mute everybody. I don't have a mute all button, but there I muted Dennis Allen, and it sounded like, Dennis, that that feedback was coming from your microphone. So turn your microphone on yourself when you want to talk or ask a question. Go ahead. Everybody's free to do that. But if you're not, please turn your microphone off. Also, if you're not using your video at the moment, turn your video off. Please turn it back on if you're asking a question, or if we need to see you for some reason. My video I have to work on is really dark in this room. I tried turning the light off behind me, but I'm still getting all the light from the window, and I don't know how to get rid of that. So I think it's a good idea, and this is advice to me, not to have light. Do not have light behind you, but do have light in front of you if possible, and then your video shows up better. My apologies. I'll have to work on that for another time. Somebody else just joined us, or I'm hearing somebody. I don't know if it's you, Nick. I'm going to try muting
Yeah,
you.
Greg, you
Yeah.
said you were chatting with me, but I can't see
Oh, I
any.
didn't. I didn't write anything. I just here.
Oh, okay.
Hello,
I
hello,
couldn't see any chat.
hello. I didn't actually type anything. Hello, Nick. There we go. There's a private chat with you. Did you see it? You can just type back if you saw it.
No,
Okay.
no, I don't have access to even any chat
Well,
at
okay.
all.
On the bottom of the screen now, my screen may look different than yours, only because I'm presenter, I'm host, and not everybody else is. So I'm not sure what everybody else's screen looks like. But mine has a hide chat and a show chat as a toggle. And I can toggle it on and off, and I can chat with any person that I want to, but I don't know how to have a public chat like we used to have. Maybe that's not even an option anymore. Maybe you can only chat privately with people. I don't know. But I just sent a real small chat to Nick just to see if it works.
Yeah, my chat option may be below my window and I can't see it or something. I don't
Okay,
see it.
what I see, and this is, we're going to need to spend some time because it's new for everybody. So if it's okay with you, Jeff, it kind of gives us a reason to give it people a couple more minutes too.
Hey,
Um,
Greg, this is Bob DeHill, sir.
yeah,
Uh, I I got the that blue box at the bottom where it says you can join the chat.
right.
When you do, there's two icons left to the left of the at the top of the chat.
Uh-huh.
One's a plus that says a direct chat instead of private. It
Ah,
says direct. The one below says group chat.
okay. And now we just had another person join. I'm not sure who it was. And oh, Joe Bova just joined, which is great. And Joe, I'm going
So
to mute you. When he joined, then everybody moved down one on my screen, and so the chat got smaller. Okay, so Bob, while you were saying that, that all happened. Uh, you say there's another window to toggle
no,
on the chat
no.
itself?
Once at the bottom, once you got that blue chat
Yeah,
box,
yeah,
uh, blue, then you
yep.
got the chat box to your right, but to the left, to the northwest
Uh-huh.
corner of that box, there's a plus sign and another chat symbol.
I don't have that plus sign. At least I don't see it in the Northwest. I don't
Well,
see a plus
see,
sign.
if I put my mouse on the plus, it says direct chat. And if I put my mouse
Huh.
on the lower one, which is another icon
Okay,
for chat, it
Bill.
says group chat.
Gotcha. Okay, that's what we're looking for, but I'm not seeing that. Now you're doing it on the chat window itself. Mine says chat to Nick Percival. Now if I pick another individual, then it'll be chat with Joe Blow or whoever. Uh,
Well, then yours is different. But
Mine
what
is
I
different apparently.
yeah, but now what I just said is apparently valid for everybody else.
Okay, everybody but me should be able to chat now. Well, people are coming. We're up to about maybe 13, 14 people now. So that's good. Um, and I know we'd have more if we had a little more alert, and also if we had just, again, the regularity of meeting on Saturday mornings. It's been a long time and we haven't met. So, but I would say I do recognize that the whole system is new for everybody. I didn't find what Bob was just talking about, so hopefully some other people can. We'll have to just play with it. Everybody, please feel free to play with it during the course of the hour and try to figure out the new system. I think the new system is really good. I think they've worked out a lot of bugs, but anyway, we'll all have to kind of play with it on our own because it's new for me too. Meanwhile, I think it's okay. We're 10 minutes into the presentation. We'll give Jeff a chance to start. I'm going to mute everybody only because Bill Lucas, I'm muting you, and ask that everyone kind of mute yourself. Those of you that don't have audio, which looks like Harry does not have audio at all anyway, so there's no possibility of muting him anyway. Everybody else is muted except Jeff, which is the way we want it, and I will turn my video off when I'm ready to be done introducing you. So Jeff got involved in the NPA kind of at an unusual time, about the same time that all the mess happened uh, with names that I don't even want to mention. But anyway, and it's unfortunate, but we're continuing on, and our group is still here, and we still have some active people, and we can pull it together again. And I'm happy to see Jeff, some fresh blood, get involved in the NPA again, and tell us a little bit about his idea for integral geometry, which is going to be new for all of us. And that's all I have to say. Jeff, take it away. And if you have any questions, please let me know. And please be patient with me as I figure out how to use everything. I'm going to disappear and come back at the end. We'll have questions, and there's a way to raise flags, which we'll get to, I guess, when we get to that time. Um, but we'll try to use the flag method. It shouldn't be too much of an issue with this few people anyway. And yeah, people will join as time goes. But Jeff, before you start, if you don't mind, give us a little bit of an introduction about yourself, how you got interested in the NPA, or I keep calling it the NPA, the CNPS, um, and on our work and everything, and then tell us a little bit of background on your own work so that we can kind of get into that. So thank you very much, Jeff. Go ahead.
Okay, thank you. Can you everybody hear me okay? Can you hear me okay, Greg? I'm assuming you can.
I just muted myself, so now it's
all right, as long as you can hear me, that's fine. I thought you might come back. All right, so let me change the slide here. My name is Jeff Baugher. My email is on the first page of the slide here. And what happened is I'm probably what you consider a former mainstream researcher. I got my double E in 2008, and I was accepted into a PhD program as soon as I graduated, which was funded by a federal earmark program. So I started studying at the Air Force Institute of Technology in Ohio. The problem was I was actually happened to deal with elastic materials and microelectrical mechanical systems. But I also happened during that time to learn about the cosmological constant problem and some of these other issues that we're having in physics. It occurred to me that there might be a solution to it, but the problem was that the solution I kind of saw wasn't compatible with mainstream physics. And as I studied more and more, about 2013, I started learning about natural philosophy and ether theories, which I didn't really know anything about. And about that time, as I realized that people who were studying natural philosophy still actually had a point. So you could say that I did a 180-degree turn from mainstream physics over to natural philosophy. And like Greg was saying, unfortunately, I joined at a time that was tumultuous in the NPA time. But luckily, in 2016, I was asked to join the board of directors, and I am happy to be here. What this research is about, let me change my slide here. The prerequisites of it is it's gonna be helpful if you've had some type of integral and differential calculus. So if you've had college level calculus courses and you understand the concepts of an integral and a derivative and everything, that would be the basis of what you might need to get really a lot out of this presentation. It's also, I mean, most of you people are experts on the history of natural philosophy and some of the arguments against mainstream relativity. It'd be kind of helpful if you did understand general relativity, but if you don't, that can also in some ways be a good thing. But if you do understand some of the historical development and stuff, that can be helpful too. What I'm trying to do in this presentation is just give a context that we can talk about something from the same type of basis. So I'm just giving initial concepts and everything with small explanations. And then I'm going to give my framework of my argument against mainstream. And then I'll get to some more specific steps. I skip over derivations and a lot of little things in the background and everything, but I have to in order to get through this presentation, and so that I can show you my logical chain of motivation for abandoning mainstream and going for natural philosophy. So I'm just going to jump right into it. All right, let's just assume that we have a line segment, and we're just going to call it B. And we're going to say it's an absolute line segment. You don't have to really know what absolute means right now. Just we have a line segment that means B. And philosophically, we equate a line segment in this research to a change, some type of change. So we can philosophically equate dB, however you want to take this line segment and squish it down to an infinitesimal size. We're going to equate it to dx. But we're going to philosophically interpret dx. Oops, somehow my thing went back. Philosophically interpret dx as an infinitesimal movement or translation. So I am infinitesimally moving down this meter stick a certain amount, and we say that's what the dx is, which is modeled after dB. And the reason that's important is that a lot of our equations, when we start to describe force, such as a directional derivative and energy, the Poisson equation, they both contain this philosophical equivalency. Now let's instead say that B is a relative line segment. You don't have to know what that means at the moment, but it has the same type of notation. We can philosophically still equate dB to dx, but in this case, dx we consider it to be an infinitesimal change of a meter itself at a point. So in both cases, we have changes. On one case, I'm actually moving an infinitesimal portion of a meter. In the second case, we're actually looking at how a meter changes at a point itself. So let's take a look at a couple of orthogonal or perpendicular line segments. We have A and B. Somebody's changed my thing. Let's just say that B is a function of A. So I can know, if I know the length of B, or if I know the length of A, I can know the length of B. So if AB is my area, then if I know how the slice of area, A times dB, changes, I can philosophically know how a meter changes as I move along by watching this little slice of area. If you look at the bottom of the slide here, you can see if I examine how my little slice of area moves, that's not a perpendicular line segment. That's actually an infinitesimal block of area. If I examine how that slice of area changes, I can know philosophically how a meter is changing as it moves along. So if I'm co-moving with this little bitty slice of area, then it traces out a constant relative area. But if I were to watch it go past, then I would see the line segment rise and the line segment fall, kind of like a wave. Now, if you can understand just that little bit there, then we've at least have a contextual basis to start at. So here's the chain of what I'm going to show you, where I have a problem. Is I'm going to present something called integral geometry, and I'm going to use a Venn diagram with 3 circles here. And there's going to be these 3 overlapping little line segments that divide up the where they overlap. And then, and I apologize to Bob DeHilster, but I'm going to bring in what I call fictional Bob. And this is a argumental device. And Bob's going to say, you know, I kind of like what you're doing here with integral geometry, but I think that we could, you're making things a little complicated, Jeff, and we can change a few things here, and we can just make our physics equations this other way. My problem is that if I look at what Bob has done here to integral geometry and how he's writing the equations and everything, I can't tell the difference between that and metric field theories, and specifically general relativity. So this is the chain of my problem is that I see kind of what Bob is saying and stuff, but it looks like he's misapplying geometry, notation, and natural philosophy. But I can't tell the difference between what he's doing and what I'm being told in general relativity. So just to give you a little bit more context, so that you have 2 things to compare, and you don't have to understand what each of them mean. It just allows you to have the ability to compare one thing to another. So I can go on with the presentation. In general relativity and gravitation and differential topology, they have this concept that if you get closer to a curved surface, it becomes more and more flat as you get closer and closer to it. So that's what they call flatness. And over integral geometry, though, remember how I was talking about the blocks of area where one side was relative and one side was absolute? The problem is that I could tell the difference between a block of relative area and a block of relative and absolute. But as I get down to making them slices of area, I can't tell the difference between one slice of area that's made of 2 relative line segments and a slice of area made of a relative and an absolute. The slices of area look exactly the same, so I can't tell the difference between them. In general relativity, we have this concept of straight lines, so that everything has to do with whether lines are curved or whether they're straight. And over in integral geometry, we have the concept of constant relative area. I can have components of an argument where my relative. All right, so back here. So I can have this concept where I have components of a relative area that are changing, but if I sum the components up, my relative area is constant. So on one hand, I have straight lines, and the other hand, I have constant relative area. In general relativity, they say, well, particles always travel in straight lines. We're over in integral geometry, and let's develop a theory where it says, well, ether waves travel with constant relative area. And in general relativity, we have these 2 concepts called invariance of a forward vector and conservation of energy momentum, which has to do with particles traveling in a straight line. Over in integral geometry, we have a concept called conservation of relative area. So basically, all I'm looking at is I'm pretending like I have a perfect fluid, and I'm examining relative changes of density and pressure, and I'm saying that the relative changes of space and time are functions of that, but they're modeled after relative area. In general relativity, we have the concept of where you can have a singularity in the space-time coordinates, and it's called a black hole. Now, in integral geometry, if you decided that you wanted to model the universe without any matter or energy as having a constant relative area, that's a bad idea for two reasons. One of them is going to be there's going to be a solution exists where all of a sudden you're going to run out of your relative area. You're going to have constant relative area, and at some point you're just going to run out. And on this is two sides of the same coin. And also in general relativity, you have this thing called the cosmological constant, where any other value besides 1 on this diagonal of this thing, if it's a 5 or 1,233,000, it's considered a constant, a scalar multiple of a metric. And over on the integral geometry side, we say, well, you still don't want to do constant relative area. It's a bad idea because at some point, instead of having abstract notation, you have to pick a value to put inside the equation. And when you do that, though, you realize your equations aren't unique. So how do you represent constant? Why do you use constant relative area whenever you don't have an exact value to put in there? And so instead, you end up basing everything off of one equation. In general relativity, there's no absolute reference frame for particles, whereas over in integral geometry, we consider a reference frame as measuring one ether wave and relative to another. Now, both of them might be governed by the same relative area function, and those little functions inside the wave might look exactly the same and stuff, which is fine if you're looking at one single wave particle. But as you grow things up, there is ways that I can argue with a new type of quantum physics that you can find an absolute frame of reference. I won't go into it, but it's way past this. So instead, my slide's changing. But over on the general relativity side, they say the speed of light is constant. And over in the integral geometry side, we have something called the relative point velocity of an ether wave disturbance. And we'll say, yeah, that's constant. But that's not the velocity of an electromagnetic wave that you and I would measure. Okay, so obviously there's going to be some differences between what I do here and what you would ask somebody at a university about mathematics and how differential geometry works. So it's going to be helpful to ignore some of the mathematics of the last 150 years, especially since Carl Gauss and Bernard Riemann. So once I get my logical chain firmed up, then we can start developing some comparisons with mainstream mathematics and where these things are coming from. But I still am assuming that everything I develop in integral geometry, I can rederive everything that's already in mainstream physics, or at least general relativity. So let's just go back to some real basics here, so that we can understand. We can have a common ground here. In geometrical calculus, an overview of it. At the top here, you see some blocks, and I am saying that I can sum up blocks of area, no problem. And the bottom, I can say, you know what? I can also find the total difference of blocks and find the area in both cases. Now, if you also consider that I can sum blocks of area, if you consider this, see the little, if over in the bottom, over on the right, you'll see f of x dx. And this is how we're commonly taught calculus. What you're conceptually doing is you're actually summing up little infinitesimal slices of area to find the total area. And that is what I would call geometrical integration, is whenever you sum up slices of area, you can end up finding the total of area. Well, there's also going to be the concept of, while we can sum slices of area, we can also find the changes of the slice of area. We can find the differences of the slice of area. So geometrical integration would tell me my total area, but geometrical differentiation would tell me how does my area changing as I go from one slice of area to the next. So that if I was to ask you, what is my total area? Then I would sum the slices of area. How does my area change? Then I would use geometrical differentiation. That doesn't necessarily mean I don't have any area. It just means that my area is not changing if my slices of area are not changing as I move. So we're going to get a little bit more specifics here. This is a Venn diagram, which is nothing more than 3 circles where we have concepts in each, and then where they overlap, we say that the concepts in one are equivalent to the concepts in another. Where all 3 of them overlap, we have 3 concepts that are the same. What's in the bottom blue left circle, this conceptually, is relative and absolute perpendicular line segments and the area they bound. And that's all it's there. There is nothing but geometry. And by geometry, I simply mean nothing more than line segments. And that is what is in there. Over on the right hand in the green circle is not what I would consider natural philosophy. Time, space, seconds, meters, energy, momentum, pressure, and density of a perfect fluid. And so far as I can tell, that's about all I need. Up in the top red circle is a written notation. If I want to write out a written language that describes what's in the blue and the green, it's important to understand to make sure that I don't have mistakes in my notation, and that I'm also writing notation so I can tell the difference between my different concepts. Whenever I put this dashed line, what I am doing is I'm splitting the overlap. So where the circles overlap, I'm splitting them. Now what happens is this is what I would call a functional or causal boundary. So now over in my blue thing, my blue circle where I had these perpendicular line segments, now I say that my line segments have some type of functional relationship between their sizes. Over in the green circle, in my natural philosophy side, I now say there's some type of causal relationship between, let's say energy or density and something to do with space and time. And up in the red circle now, we would write out a functional relationship. So, but where the boundary is I'm saying that one functional relationship in geometry is equivalent to a type of causal relationship in natural philosophy. And I use written notation to describe both of them. A good way to think of it is that natural philosophy is I have these clothes and everything, I have these concepts, and I am hanging them on my framework of my geometry. So I'm looking at how does relative area change and everything. And I'm using the line segment as changes, and I am examining how this relative area changes and seeing whether or not that is a good description for nature and how nature works. Let's talk a little bit about tensors. So in integral geometry, a tensor, you can arrive at tensors by splitting the concept. Instead of splitting the circle here, instead of splitting the overlap, I'm now splitting the green and the blue circle. In integral geometry, a tensor is an equation where I mix natural philosophy and I also mix geometry into one equation. And that is normally how Newtonian physics is taught whenever we equate like Newton's law of gravity and everything in type of a geometrical tensor form. So just to reiterate what I'm talking about here, we have three circles and there are three conceptual regions. They each have their own little components, whatever they are. One of them is natural philosophy, we have geometry, and we have written notation. Where they overlap, I'm saying one thing, I'm writing notation and I am describing geometry, or I'm writing notation describing natural philosophy. Where they all three overlap, I have three ways of looking at one thing. If I write the line segments in the middle and overlap everything, I am saying the functions in one, or the causal relationship in one, is the same as the functional or causal relationship in the other. So we're going to look a little bit again about tensors. In mainstream Newtonian physics, we often convert things into what I would call a tensor form. If you've ever seen a directional derivative or Poisson equation, if you look down at the middle of the equation where I have the d phi and the dx, you will see the d phi is a geometrical argument. The dx is a philosophical argument. And it's a mixture equation based on geometry and natural philosophy, because you're considering in this equation dx could be considered as an infinitesimal displacement, but that's just a philosophical way of looking at dx, and it's actually a philosophical way that we're examining area. So we're going to borrow this concept of a tensor of a perfect fluid. And what this allows us to do,
Hey Jeff, I'm sorry to interrupt, but I know that you probably defined them, but somehow I missed, and it would be a good idea if you don't mind redefining Gensers and fencers. I know what tensors are, but I don't know what Gensers and fencers are.
Right.
I just thought I'd ask now, so there may be others in the same boat.
Okay, let me go back to it. All right, so a Gensur, and I know it's a cheesy word to say it, but a Gensur is a way of looking at perpendicular line segments. Are the perpendicular line segments functionally related? You can have two line segments and have area, and there's no functional relationship at all. But if they're functionally related, if one line segment, the length of one is related to the other, that is a Gensur. So a fencer is a philosophical relationship between, let's just say, something to do with time or space or something, and something to do with energy or momentum. So if you've ever, and I'm jumping out of integral geometry, but if you ever heard that, matter tells space to curve and space tells matter how to move and everything, that is another theory's way of describing a causal relationship. So in the same way we have here, we have a fencer, is that we are describing a causal relationship between a change of one thing, the relative change of one thing, and the relative change of another. But it's philosophical. So a Gensler is purely geometry, purely looking at nothing more than line segment changes, and a fencer is nothing more than a philosophical relationship, a causal relationship.
Okay, so Gensler, G is geometry, and F is philosophy. Is that right?
Yeah,
All right,
exactly.
That's what I'll remember. Thank
So
you.
hopefully it seems like a cheesy way of looking at it,
Okay.
or saying it, but I think it maybe helps people remember it. So let's go back here. Okay, so we have this thing called a tensor of a perfect fluid, which is brought out of mainstream physics.
Jeff,
Okay, so
let's go back to that drawing where, I think you defined a tensor incorrectly. There, back.
This one, back
Yeah,
one, this one here.
That equation is wrong.
Why is that?
Right in the middle where it says d phi dx divided by dx dx. That's not right.
Oh, that's not right. Does that not simplify down the d phi dx? So what I'm doing is I'm simply saying the numerator.
Here in this equation? What does this equation mean? This doesn't mean anything to me.
Do you know what directional derivative is?
Yeah, I do, and that's not. I don't know what you're doing there. What are you doing?
I'm simply saying in the numerator part you have a d phi dx, right?
All you did was multiply dx in the numerator and dx in the denominator, and then cancel them out.
Yeah, exactly.
That
so on the top of it, the numerator portion, you are simply.
I'm sorry. You can.
I didn't hear what you said.
I said I don't understand what you're talking about.
All right. Well, let me get finished with the presentation, then we can go back.
Sounds good. Thanks.
All right. So going back to it, we have this concept of a perfect fluid, and this we can now track. Let's just say that we can use a perfect fluid. We can track changes of density and change of pressure via the velocity of the changes. So what we want to do is take this tensorial form of a perfect fluid, and we want to hang it onto our geometry of two relative line segments. So we're taking our natural philosophy portion, and we're modeling the density of the perfect fluid. We're going to have something to do with energy density, and we're going to model the pressure of it. It's going to have something to do with momentum. Now, through the point velocity of this perfect fluid, where I can equate x, I can also say that we now have something geometrical, the b, which has to do with the philosophical x and the LT, and we're going to talk about relative point velocity. So we can introduce the concept of time through the evolution of the perfect fluid.
Okay, hang on. I'm sorry to interrupt. Somebody is not muted, and I don't know who, and I don't know. I've unmuted everybody that I'm able to reach, but there may be more, and I don't know how to reach them. So, okay, whoever it was unmuted themselves. Thank you. Sorry.
Okay, so it's important to understand let's talk about a little bit about the time portion up in the top right, where we are having something to do with x, and that equals LT, where L is my velocity of the disturbance in the fluid, and we have this T, which has something to do with time. If you look down at the bottom left, I have A times dB, which is a slice of area. If I hold that relative slice of area constant, and I am basically taking a partial derivative, I can then say, well, I'm also holding the rate of change of a meter constant, and I can also say I could also equate that to holding the rate of change of time constant. So a partial derivative of an argument with time in it, it doesn't mean I'm stopping time. I'm just holding the rate of change of time constant. So on one hand, I'm holding the relative change of area constant, and the other, I could argue that I have an argument where I can hold the rate of change of time constant. And there's a little question mark that's in my equation, and I'm simply just saying there's something logical which would fit in there. And going back here, so now we want to, what we're saying is that we're using the properties of relative line segments and relative area, and we're going to equate those to some type of known physical property, such as conservation of energy momentum, to see whether they match observations and whether the relative area and natural philosophy is a good description of the natural world. And so on the left-hand side, I have a red and a little blue circle with the A in it. And what I'm saying, I am notationally writing an equivalency to a line segment. I'm equating that philosophically to the change in density of a perfect fluid, which I notationally write out as a rho. And in the bottom, I have another line segment B, which I am saying is equating that to philosophically to the change of a meter, which I am writing on the right-hand side as an X. So, and these are all philosophical considerations, so you could argue about what they exactly mean. But the equational analysis, even of a directional derivative, gets too complicated for an introductory presentation. So I'm not going to go through all the equations. But let's imagine on the top right, I have this little matrix here. And all it is ratios of line segments of A over line segments of B. And I'm looking at the squaring of them. So I'm looking at the ratio of one area over the ratio of another. If I hold the relative area constant of this top left term, I'm taking a partial geometric derivative. Then the only thing that's going to matter is the top row, because that's the only row where these B's that are in the bottom are functions on this row are functions of the A. So we only have to consider the top row. And I'm taking a partial geometric derivative. What I am doing in the philosophical portion of it is I am holding the density of a perfect fluid constant, which means I am holding my rate of change of time constant. If I do that, then it ends up has the same form as Poisson's equation, which means that I am having a hard time telling my slices of area apart. And that is why we say, or at least in this is where I am saying that Poisson equation, or some concept of energy density, is a partial derivative of this matrix of equations. And the whole basis of it is that we are looking at relative slices of area to describe nature. Now, this is the, obviously this is probably pretty difficult at the beginning. I'd have to go back over and explain little pieces of it. So let me just launch into what I'm going to call fictional Bob, and apologies to Bob DeHilster. But Bob says, I see what you're doing with the relative line segments, but he says, I don't think you need gensers and fencers. He said, they're unnecessary. I think you only need tensors. So he wants to abandon the concept of relative area and just stick with taking derivatives. But he does like the concept of utilizing a perfect fluid. And he also likes the concept of keeping a relative velocity of the disturbance in the perfect fluid constant, but he wants to call it something else. So Bob goes back to what he considers to be tensors, and gets rid of my gensers and fencers. And Bob says, but we still want to use a relative and an absolute line segment, and he still likes the concept of two relative line segments, how they work. But he wants to get rid of any concept of a gensor or a fencer. Now, Bob, what he's going to do is, over on the right-hand term where I have integral geometry, I have one equation that's nothing but line segments, a ratio of one line segment over the ratio of another line segment, the squaring of them. And he's going to equate that, I equate that to the ratio of the change of a perfect fluid and the ratio of the change of a meter at a point. Bob says over on the left, he says, well, I'm going to mix those two equations up. So now he has geometry, the d squared a over something philosophical, the dx squared, and he's going to equate that to something philosophical over something geometrical. But he's going to get rid of the rho. He doesn't want my using my perfect fluid point equation right there. He wants to go back and use a phi there. So we now have d squared phi over db squared. And he calls that the Poisson form. So x can equal, let's say, LT, which means space and time, and the a and the b's are nothing more than geometry. So Bob states that by changing rho, And with the way I was doing stuff, he can now look at how I'm going to end up changing x over in the far right equation, since we now know that x changes with respect to either of the geometry. Whereas I would say in integral geometry, this is actually just a property of relative area. And Bob says, if you look at the bottom equation here, see where the a dB is, and I have the two dx's? He says, if you keep that a constant, he says, then my dx's are going to, you can't tell the difference between whether they're absolute or whether they're relative. They're going to end up looking just alike because you're holding the a constant. He refers to this as being flat. And he says, well, we can now say that space and time and geometry are interchangeable. If you look through how this equation evolves, it's probably going to be a little bit too obtuse to go through it, but if you want to come back to it. But essentially what I'm saying, where the a argument is in the numerator, if that's a constant, then, and I go from point to point, then obviously my dx's aren't changing. And so obviously the length of a meter is not changing as I move along. And Bob says by backward analyzing how the geometry changes, of course, then you can see how it would end up changing the row geometrically. So Bob says, well, from his observations, it appears like the universe is flat, and it looks like so it's difficult to tell the difference between whether dx is absolute or relative. So what he wants to do is he wants to take the limiting value of his geometry, the independent variable, to be a constant on the diagonal of the matrix. And all that means is that the relative area is not changing. That's how integral geometry would view it. Whereas Bob would say, well, it means that the universe is flat. Since my dx isn't changing point to point, obviously I'm not changing my meters from point to point. So as we look at this little diagonal again here, these little slices along the diagonal here, he says, are constant slices of area. The independent variable is constant. And Bob says there's no area on any of the other portions everywhere else. And to reiterate, the problem that we would have with that is that if he decides to take a partial derivative again, so he holds the top left of this argument constant, if you look at the top, the a0, db0, and he holds the independent variable constant, well, he can do that. But that means at some point, as I approximate this, he's pretending like he can see the whole waveform or the whole area at one time. But at some point in his area, that first, where he's got a constant there, that second term, where the dB1 is going to end up equaling the same as the first one. That's going to be an issue because now you end up running out of relative area at a sharp point. The second part of that is that using Bob's understanding of using constant relative area is that well, let me go back to what I was saying here. Okay. Somehow my slides are changing on without me doing it. He says, well, that's not a problem if I run out of relative area. He says that's just a point where electromagnetic waves can no longer propagate outward. And that's Bob's argument of what that is. And that's a real physical phenomena. If you run out of relative area, that's not a problem. He said that it's going to end up being a singularity in your space-time coordinates. If you look at the bottom two equations on here, you will say, well, if my row here, whatever it is, gets too big, it changes my geometry. And if I look around the right, as the arguments get bigger and bigger, obviously I'm going to have some point where the point outside the two dx's is going to equal a 0 as I sum up the terms of the independent variables. So just all you have to remember is that somehow I'm going to run out of relative area when I sum up the terms of the arguments. So we asked Bob, okay, well, you have on this diagonal all constants. So when the abstract notation goes away, you have to pick a number, some type of numerical value to put in here. What number would you use? And Bob simply states, well, he would use a 1, because when he writes it in the equation below, so he can substitute out the a, if you look in the middle part, we can simply say we have dB, and that is going to equal what he says is philosophically the dx dx. So if you examine how the geometry changes between this dB, dB, it says, well, it makes it a lot simpler to just use a 1 here. Because now you can simply do it away with it. If you write a 1 next to any equation, you don't have to write the 1 in. He says it makes it a lot easier to understand. But the problem is that we know that for constant area, any constant number will do. And Bob says, well, I'm going to bring that back in on the back door, and we're going to equate that extra constant value as energy density at a vacuum as a constant pressure. He has no real good other reason why his equations are all based off of 1 instead of the constant and the diagonal. Let's just compare a little bit about Bob's understanding of geometry and what general relativity says. So in general relativity, you have this ds squared equation where you have what's called the metric, and you multiply that by dx dx. In general relativity, if you change the g mu nu, you are looking at the change of space at that point. But if g mu nu is constant as we move along, then dx dx does not change, just like how we think of it as a scalar field. So basically, on one hand, dx dx looks like a constant slice of area of a relative and an absolute line segment. On the other hand, it still looks like, if it changes, then you look like you're changing the relative area of two relative line segments. That equation seems to look awful similar to Bob's. In addition, on general relativity, there's something called scalar multiple of the metric, where this is any other constant value out there. You don't see this middle equation much, if at all, but the reason is because it's not written out because it doesn't make any sense, but it does illustrate the problem in general relativity of why would you add have some type of constant value other than 1, yet it still represents flatness. If you compare that to Bob's argument where we could throw any constant number into the side of a rectangle of a relative area, and it still doesn't change how my relative area is changing. And over in the general relativity side, when we do the approximation of what they call to the Newtonian equation, 1 minus 2 phi, at some point, phi is going to equal 0.5, and you're going to end up with a 0. You could have a singularity in space-time coordinates. Whereas over on the left hand, on Bob's side, you have two components of his argument, and at some point, you could have where the independent variable argument equal each other, and you still end up with a 0. And that's a problem if you use using constant area as your basis for what the universe looks like with no matter or energy. What this presentation hopefully for is to provide me some feedback on ways that I should try to present this and as I develop this and go along. While you may not like what I'm doing here and it may not make a whole lot of sense to you, this is about the first half of my stuff. I also have another physical experiment that I'm proposing where I say that ether wave theory can answer an old physics paradox. And I'll be talking more about that at our conference in July. So hopefully if you get a little bit out of this presentation and you have and it makes any type of sense to you at all, then you would be able to, we can talk about it at the conference if maybe one or two of you show up.
Jeff?
Yeah, go ahead.
This might be, again, it's totally up to you, but it might be a good time to open things up for questions, and then you can continue with the second half at another later, unless you want to just go right into it.
There's no more slides. The other stuff I'm going to end up talking about at the conference. I don't have anything more to say about it right now. I'm not ready to present that. So right now I'd like to just open it up for questions.
Okay, super. Well, I have a couple questions, and I can't figure out how to get my video turned on. I only have mute, and I don't. Oh, I know. I remember. Okay, I forgot. Yeah, it's down at the bottom. Okay, and my video is no better than it was before. But okay, so well, first of all, thank you for sharing. It's been probably a year since we've had anybody share anything, so it's great to have a new face, and I appreciate that. And I do like your concept of Gensers and fencers. I'm sort of still trying to get my head around it. But I guess what it reminds me of, and I'm sure this is probably not what you were thinking, but there was a time, maybe 200 years ago, when electricity and magnetism were considered two completely separate sciences. And Maxwell had the genius to say, hey, they're really one and the same science, and we can merge them. And so, since then they've been merged. But so so maybe to go the other way isn't such a bad thing, because we can say, all right, we want to see that whatever these objects you're calling Gensers and fencers are, they are different, at least mentally different. There's a geometry side to things, there's a philosophy side to things, and then there's the actual mathematical side to things. And maybe we need to go back and say, at least for a time, that they are in fact different, and then here's ways in which they are the same, and that's your Venn diagram. So I applaud you for thinking in those terms. Not quite sure yet what to do with it, but anyway, I thank you for bringing that out. So
Okay.
that's just an observation, not really a question. Anybody else? I don't think we need to do flags. Just go ahead and get up there and speak. If we had 50 people, we probably would. But yeah, if anybody wants to just jump in, please. You turn your video on from below, and you turn your audio on by unmuting yourself, which is
Jeff, this is Harry Ricker. Have you looked at Heston's work? David Heston's, you ever heard of him?
No, I have not.
Well,
If you could write it into
the
the
problem I have here with what you're doing is it looks to me like you're reinventing the wheel,
Mm-hmm.
and there's there are different kinds of geometry out there other than just general relativity.
Right.
And people have been trying to get the physics community to go away from the traditional Einsteinian view of general relativity, and not very successfully, if I might say. That seems to be what you're trying to do. Am I not correct? Is that your objective? I'm not really sure what your objective is.
My objective is to say that the my objective is simply to say all I'm doing is I'm looking at relative line segments, perpendicular relative line segments. I'm looking how they're functionally related, and all I'm doing is comparing how they work and studying how they work and comparing that to how they say that general relativity works. How we can take a particle and what these concepts of what they're saying and what these equations mean.
Let me stop you, Jeff.
Okay.
Relativity is based on an invariant concept, and tensors are based on that invariant concept as well.
Right. Right.
So tell me what your invariant concept is, if you have one.
Invariant concept in this is constant relative area. The relative area does not vary.
I don't know what constant relative area means. I'm sorry.
Right. I understand. If you say that, well, if my relative area changes, then you could say that my dimension of time and space change.
I don't know what relative means. What is relative? That doesn't mean anything. The word relative confuses me. Okay, relative to what?
Okay, so I have one line segment that changes relative to another line segment, and that would be the basics of what I mean. So a line segment represents a change, and I'm looking at one line segment relative to another. One line segment philosophically relates to something else, and the other line segment philosophically relates to something else.
The problem I have is I'm not sure whether you're saying the area is the invariant or not.
So the little components of area do change. So the relative area of one component will change, but the change of the relative area in the other will offset it. So if I look at the sum of the two, though, the total sum is invariant.
I don't get it. I'm sorry.
Okay. I'd have to, I guess, write out the equation a little bit more. If I have one, just think of it this way: if I have one block of area change,
you talk about philosophy, but the philosophy that mainstream is operating on now, which is the relativity philosophy, I guess you could say, is that there's this invariant, and they're saying the velocity of light is the invariant. Right. So they write these multilinear algebraic equations that are basically tensors, and they create a law of invariant change so that the velocity of light is always the same no matter what coordinate system you measure it in.
Right.
That's my understanding of what mainstream is doing. So if you're going to substitute something for that, then you would have to explain kind of what your invariant is and philosophically why that invariant is superior to the invariant that mainstream is using.
Okay, that's a good point. I would have to come out with, I guess, a simpler way of explaining it without having to, but how do I do that without introducing relative area and going through the basics of
I'm
it?
not really sure what your primary.
My
See what.
primary goal is to show that this concept of relative area can produce similar equations to general relativity, but that if you changed how I'm doing this, you
What's
would end up with the same problems.
relativity basically is an attempt to, well, I don't special relativity, but essentially what Einstein did was he tried to resolve this issue about the Michelson-Morley experiment, if we are to believe the propaganda. And he created this invariant that's the velocity of light that's invariant. Okay. And then all of physics has to conform to that velocity of light invariant. So there's a physical concept there. The problem with velocity of light being an invariant is that it's a ratio of space to time.
Right.
So that doesn't really solve a problem because is it space changing or time changing or both changing, and how are they changing? And so now you got all this tensor stuff. Okay. If you had some physical quantity that you could measure, like energy or mass or something that you could pin down as an invariant, that would be better than having something that we don't know what it is, space and time changing.
Right. Well, we both agree that we're just talking about ratio of a change of space and the base of time. I agree wholeheartedly with you on that. And that also, so, but if you look at it, you can also think of it geometrically that I am looking at a slice of area over a slice of area. I know it's a little bit hard. If you look at it long enough, you will see that the bottom portion we are equating to this bottom portion of this infinitesimal slice of area, we're equating that to a change of space, and we're equating the other one to a change of time. But that doesn't necessarily mean that that is the velocity of an electromagnetic wave that I read on a clock. I'm saying that what I'm saying is that yes, that there, I don't mind that being a constant, but that is not exactly what we're talking about when we measure the velocity of an electromagnetic wave on a clock. Because in the way I view it, the way that looks like the equations will happen is that depending on how fast I am moving, I can have two clocks that tick at the same rate. But as I go faster and faster, the clocks start ticking at different rates. But so if the clocks end up ticking at different rates depending on my absolute velocity through whatever you want to call it, I don't understand how the velocity of light can be considered to be a constant.
Okay, I got you. Okay, so now we're getting down to the crux of the matter, which is you're basically getting at what really is the philosophical problem with special relativity to begin with. And you have an intellectual difficulty making sense out of what the claim is that underlies the physics of relativity and mainstream physics altogether, basically, is what you're saying, right?
Right. I'm saying I see the point where you're saying you have this constant velocity here, but I have a problem with philosophically saying that's a clock that I am measuring and a rod that I am measuring an electromagnetic wave with. I'm saying they are not, I don't believe that they're the same thing. And I think that I can present a logical chain of
Okay, that's interesting. It would be better if you gave a little more preliminary discussion of that so we could understand it more
okay.
rather than jumping into the math. That would be my comment.
Okay.
Because
Right.
I think what you're saying, it gets to what you just said about time and velocity gets to the fundamental issue that people have with relativity. It gets to that that it it's not very satisfying, and it doesn't really make sense to people. But they can't really pin down exactly why it's wrong. You're trying to pin down a new way of looking at it so that you could basically say this is a better way of looking at it than the way that you're looking at it.
Right. So I can give you something, a little specific concrete example, and we can narrow it down to say I have either this choice or this choice, and this is where we cross the line. Which one do you believe? So I'm just trying to narrow it down to a better philosophical and
Right. So I think you need to start at that beginning point more and not jumping into the math, because the math, I think people jump into the math, and that's what Einstein did. And what he did, and I keep trying to explain to people, the math that he came up with is wrong. And because that math is wrong, you've got a lot of the paradoxes and the problems that people point out, but they get ignored because people want the philosophy to be right. And so if you make the philosophy right, people like that philosophy of relativity and Einstein. But the problem is when you try to implement that in the mathematics comes out wrong. Okay. So jumping into the mathematics kind of like is the same mistake that Einstein did, which he thought, oh, I'm smart, I can make this work mathematically, but he didn't. And so you got to be careful about that.
Okay.
If I can jump in, Jeff, Harry, early on in your conversation with him, recommended David Hestenes, and I don't hope I'm not butchering his pronunciation, but
I think
I
it's
recommend him as well. And the two books that I found the most helpful, which you might want to write down, were not by David himself, but by a guy named Alan MacDonald. And the first book is called Linear and Geometric Algebra, and the second book is called Vector and Geometric Calculus. And they're both about 30, 25, 30 bucks. And I highly recommend them both.
I own many books on both on vector and analysis and all historical. I mean,
Okay.
I have this book here is like $300, and it goes directly into all of that. So I understand where we started off at, and I understand when we talk about vector analysis. I don't talk about vectors at all because I'm dealing in the basement and everything, and you would have to re-examine what do we mean when we equate a directional derivative to a vector concept. There's also a philosophical argument there.
Sure.
So
I didn't mean that as an insult, just trying to be helpful.
okay. Sorry. Okay.
Sorry if I was doing
what
that.
I'm trying to point out to you is what people have done is they've sort of what Einstein did was he took this philosophical concept that says the speed of light is a constant and every inertial frame is equivalent. Okay, so now you've got all these inertial frames that have relative velocities and they're all supposed to be equivalent. Well, what happens is that doesn't work out in the mathematics. Okay, it kind of looks like you can make it work out in the mathematics, but it doesn't. And then when people said, no, this doesn't work out in the mathematics, they said, no, we don't want to hear about the mathematical problems. We only want to focus on the philosophy that we really, really like. Do you understand what I'm saying?
Yeah, I would say.
So kind of what you have is you have people who are trying to impose mathematics on the world because they like the philosophy that mathematics works with.
Well, they like the philosophy that the speed of light is always constant because the mathematics that they're using back it up. So as long as you consider that term, the velocity of electromagnetic waves,
it doesn't really back it up. It only appears to.
I would say so. I would say you're correct because if you can come up with a different philosophical argument where you can write different equations, but which are they end up saying the same thing, but they don't agree with it, then you have a way to counter argue.
Right. I understand that point. That point's problematical too, but
I believe Dr. Lucas is in the wings, waiting to have his say.
I'm sorry.
No, that's okay. I just want to make sure everybody knows.
Is it okay for me to talk now?
Absolutely.
I think I can explain what Jeff is talking about in fairly general terms. And so in order to understand this, I want to first of all talk about the physical ether. The ether is a fluid, and the fluid could be of many different types. It can be a field, it can be, water or gas or, many different things could be a fluid. And if you look at the work of people like Winston Bostick, who discovered that particles all the particles in nature are solitons, which are standing waves in the fluid. And so if you look at it that way, instead of looking at nature as being interactions of particles, but you look at it as standing waves in a fluid, you're going to see that the kind of geometry that Jeff is talking about is really related to the ether, and it's looking at the universe more in terms of the properties of the ether than it is the properties of particles. Now, special relativity theory is a particle theory, but general relativity theory is more of a fluid geometry-based theory. And so you see, it's general relativity theory is an attempt to expand upon the defects of special relativity, and but it didn't quite make it all the way because it couldn't explain the quantization of gravity. It couldn't explain a number of things, and also special relativity theory was incomplete because it only involved the radial and velocity terms, whereas there's acceleration terms and DADT or radiation reaction terms. Those are missing from special relativity theory. They're also missing from Maxwell's equations. So all of those are incomplete to some extent. And but I think what Jeff is doing is he's able to see mathematically that there is a more geometrical aspect to the universe, and he is trying to explain that and some of the ramifications of that. And I think if you look at the universe as being made of a fluid, I like to call that fluid the electromagnetic field, but other people might have some other idea for it. But if you look at that, then particles are just standing waves in the fluid, and a soliton is not a temporary standing wave, it's a semi-permanent standing wave. And so that's what Winston Bostick discovered in the laboratory. The soliton is the strongest structure known, stronger than an elementary particle, stronger than a nucleus, stronger than an atom or a molecule. And so you can smash those things apart, but you can't smash a soliton apart. In fact, that's what he was trying to do, was build a bottle out of solitons so he could contain controlled thermonuclear fusion, because most materials just come apart when you try to build a bottle or container for that type of process. So anyway, that's my contribution. I think that if we look at the notion that the universe is consists of some type of fluid and particles are standing waves, semi-permanent standing waves in that fluid, then the approach that Jeff is using is very descriptive of that. But the approach that other people are using, which is particle-based, I mean, like if you have standing waves in a fluid, you don't use a point particle approximation. You don't do any of those things. You know, you have a little bit different approach, and so you're not going to end up with exactly the same equations like special relativity does.
Okay.
Could I say something here? I'd like to say something. This is Harry Rickard.
Sure.
I think the problem is that it's been 100 years since Einstein, okay? And Einstein kind of had an interesting idea. But what we're doing is we're kind of constructing the universe based on idealizations like that come out of mathematics. Right now, we're talking about a geometric idealization. But it's not based on any empirical evidence. Where is there empirical evidence that you're using, Jeff, to base your mathematical system on? Isn't that what science should be about?
Yeah, and what I would say is that, what I'm basing this on is to develop this framework of basing our equations on geometry, of taking this philosophy of what is space and time and what is, if we're modeling things after a perfect fluid. And what I'm looking for is properties of this theory of how this works, whether those, all of these, not just one thing, but all of these properties have any type of predictive correlation with how our universe works, with how gravity works, with how light travels, all of these other things. So it's I'm not looking for to say that I can predict this one constant, although I think eventually it might be able to. I'm looking to say that what we see out in the universe, how things move and everything, all these patterns, the way these stuff happens, seems to match how integral geometry works. And so that is where I am saying that yes, in order, and actually, and even in order for it to be any useful at all, it would have to predict something that we see. If it doesn't predict, our real world, then it's of no use. So that would be where I'd be going.
Yeah, just to sort of keep reiterating on this. It sounds to me, and Bill just sort of presented this idea, which he says that particles originate out of the fluid. So that's kind of a you're. I guess I'm getting off the track here. My point is to get to your presentation. What I would like to see in your presentation is I would like to see what you just said in more detail about why integral geometry is an idea that you think arises from the empirical knowledge as you understand it. So, in other words, what you're saying is I look out at the universe and these are the things that I see, and this is how I am trying to interpret them in terms of geometry. That's not really present in your presentation.
Okay. Well, so let me ask if this would be more descriptive, where he talks about a fluid. Um, so
You start off with here's my point. You start off with the mathematics and then dive right in, and you don't really give us much of an introduction to why you think this mathematics is correct or important.
Well, I probably need to go over a little more because these things that are in general relativity, and what I do is I assume that general relativity is a very good approximation of integral geometry. So that is why I'm kind of convinced is that the mathematics of this looks a lot like general relativity, and I think that general relativity is a good approximation of what we're actually doing. So, and to give you an understanding of the geometry, so if you have a perfect fluid and it has no density or pressure changes whatsoever at any point, then there is no relative area at any point. Once you end up with a change of relative density and pressure, you end up with a wave there. You can end up building a wave equation. Well, that change of density and pressure looks like the same thing as a relative change of area. They look just, to me, they look the same. So that if there's a wave existing there, you have relative area there. And if you have a change of density and pressure there, you have a relative change of space and time at that point. So, but if there is no change in density and pressure at all, it's just a straight fluid and there's no changes whatsoever in it, you have no relative area in it. That's how I view geometry as opposed to view, like what he's talking about, standing wave.
If I can interrupt, there are two people still waiting in the wings, at least that have turned their microphones off, and that's Dennis Allen and Nick Percival. So I'm assuming both of them want to make their comments or questions. Can we let them go ahead, and then maybe if there's still time later on, Harry, you can come back? So Dennis, why don't you go first if you're there, and then
Yes.
Nick, you can go next.
I'd just like to say that J.P. Wesley, in his book Scientific Physics, about 8 years ago now, I guess, in chapter 1, he gives a whole chapter based on proving that Newton's absolute space is correct. There is a absolute reference system, as I think Jeff said, and all sorts of experiments. It's not a theory as much as experiments showing that the concept of Newton's concept of absolute space is correct. And I recommend that if he wants to pursue that, to get that chapter 1 as it's it's just full of experimental evidence of all different kinds. And Wesley didn't believe in anything crazy like a photon goes through two separate slits in a diffraction grating at the same time, and so on. There's nothing crazy like that in Wesley's physics.
If I can interrupt, I'm going to bet that Jeff has never heard of Wesley. Wesley was a former member of the
I'm
NPA.
familiar with the dual slit experiment, but I don't know.
No, I know that. But Wesley was, let me just so you know, Wesley was a member of the NPA. Wesley was a very prolific author, and I have all of his books, and I'm betting that you don't have any of those.
No, I do not.
There's about 8 or 9. There's about 8 of them, I think. And then another author who's kind of comes from the same place is Stefan Marinov, who wrote about 12 or 15 books, and I've got them all. And we are trying, I've been trying to get permission to copy them and put them up online, because nobody anywhere has these books. I mean, they're hard to get a hold of. That's just a fact. And they're excellent. They are wonderful, terrific books. And they really almost should be introductory reading for people who are in the NPA. My problem has been I haven't been able to get a hold of anybody. I can't get a hold of Stefan Marinov's brother, and I'm trying to do this the right way. And I could just maybe copy them and throw them up there, but I haven't done that yet because I've been trying to get permission. And anyway, it's a couple of sets of really, really good books, and it's a shame that not a lot of people have access to them. Denny does. Denny's been around a long time. So is Dr. Lucas. That's all I can tell you is that if you read Dr. Wesley's book, I can almost guarantee that you'll find some things you haven't seen before. I can guarantee it.
Okay, if you can give me some names.
Yeah, and I wish I could. It's not like you can find them easily. That's the problem. They're so I'll just leave it at that.
You have to get Wesley's books from his widow, who is in Germany, used formerly West Germany. And I can give you the address here. I guess I don't have it at the moment. But you can go to the NPA website, get Wesley's old address, and then address the order to Mrs. J.P. Wesley.
She has to be 90 something, right?
Yeah, but I think his son Benjamin Wesley published the books. Publishing is terrible; the pages all fall out. But he didn't have any money, probably.
Yeah.
But I think if you send to his widow in Germany, if she's doesn't get it, Benjamin will get it, and
But we need to get that published. That's the main thing. Because they're not making any money off of it. It's not that I want to take money out of their pockets, but they're not making anything off of it anyway.
No,
and I'd like to see it put up online. All I need is for his son or his widow to say, yeah, go ahead and do it. That's all I need. That's all I'm asking for. And then we can, we'll find somebody to do it.
Which book are we talking about?
All of his books. He's got about 6 or 7.
He quoted chapter 1 from a specific book. What book was it?
Scientific physics. Selected topics in scientific physics.
I can't hear you again.
Selected Topics in Scientific Physics is the name of the book that Denny's quoting. I could go get it if you want me to show it to you. I have it in my basement.
I couldn't hear what he was saying. He was talking.
I'm sorry.
Selected Topics in Scientific Physics is the book he was quoting.
Greg?
Yeah.
This is Bill Lucas. If you go on to the Library of Congress, or the patent office, or not the patent office, copyright office, you can see if the copyright has expired on the book.
Well, copyrights generally last for what, 70 years for a book?
No, 29 years.
Okay, well, they're still not. He died in 2006. I know that.
Yes, but when was the book published? Like 1980?
Less than 29 years ago.
Oh,
I don't know where you're getting 29 from, because I thought it was 70 for books.
Yeah. You can republish at that point, and you don't need permission from anyone.
Okay, but I think we could get permission if they just said, I didn't know the 29 years. Could you send me a citation on the 29 years? Because I always thought it was 70.
Well, you can renew it.
If they didn't renew it, then it's
renew it.
Probably not.
You have to renew it after 29 years.
Oh,
And
okay. Well, it
so,
hasn't been 29 in his case. Marinov is close. Some of his stuff was written in the 70s.
yeah,
Some of it was in the 80s, but
yeah. I'm republishing the book, the writings of Hooper in a book, and they
I don't
were
want
all
to. I
published and
just want to put
copyrighted.
him. Yeah, Hooper's was in the 60s or 70s, early 70s.
Well, it
Uh,
just expires this year.
yeah.
I've
Okay,
got
that'd
the
be great. We
address.
need to get that stuff up online. That's what I want, is to make all that. I'm sorry, Jeff, for taking time on this, but
You're fine. You're fine.
anyway, that's there's so much stuff that's not up there yet. It's just it's pathetic, and a lot of that's the reason for a lot of it is we can't get a hold of the people, or we can't get them to say, yeah, go ahead and publish it. You know, that's all we need is just, yeah, we need somebody who has the authority to say, yes, you can do that. And I didn't know about the 29 years. I'd really like to know that. I'd like to see it in black and white, because I want to be sure that we're doing it right. I'm trying to do this correctly. I really am. I just I don't always know.
I'll send you the link, which shows you the copyright expiration.
Great, that'd be great. We'll definitely take a look at that. And it's a big job. If anybody wants to help, I can think of at least a dozen authors who are in that same category.
Jeff,
And I know Nick is waiting too, but go ahead, finish, Dennis, please.
the address to order the books from is Dr. James Paul Wesley. That's Wesley. And then there's a German word. It's WEIHERDAMMSTRASSE 24
I don't
78176 Bloomberg, Germany.
remember he lives in Bloomberg.
Did you get the numbers and everything?
Yeah, you said it was so it's
Dennis, why don't you email him? Email Jeff.
Email his wife or his son if we can talk.
Wesley didn't go with computers.
Yeah,
He,
a lot of them did.
all this stuff is, and
Can you
I
type
don't
it in
think
the chat room?
his wife is 80 or something. She isn't into computing.
Yeah, I know. That's the problem. That's the big problem.
But the street is Weyerdammstrasse 24 78176 Bloomberg, Germany.
that would be his wife then, who is still living.
Yeah, it would be Mrs. James Paul Wesley, you might say, instead of Dr. James Paul Wesley. But probably Benjamin, his son, will probably end up getting the thing. And it takes about 6 to 8 weeks to get your books.
Okay.
Yeah. I know I did that years ago, and I know it's possible to do it that way. I don't know how many copies they have left. You know, it's not a lot. You know, they're not bestsellers. Anyway, Nick, did you have a question or comment? I know you had your microphone off earlier.
Yes, most of it's been covered already, but I just wanted to say I like Jeff's approach, and I was thinking that the critical thinking community has not had a great impact on mainstream. And mainstream is always talking about how beautiful general relativity is, and they love Riemannian geometry and whatnot. So, and the critical community has been saying there's this and that problem, and here's this and that alternative. But I think this is a new approach that might have some impact on the mainstream, as they can evaluate it on the same playing field as they evaluate general relativity. It's a different geometric view. So I think there could be a lot of potential in this type of approach.
Good. That's
and they might be more receptive to this type of approach.
I think we need to consider that, not just because there's more than one way to crack an egg, as it were, more than one approach. And we have to consider what's going to appeal to the audience we're trying to reach. And we are trying to reach a larger audience and have not been successful. We have to admit that. And so what do we do? And maybe you're right, Nick. Maybe that's a place to go. So maybe the two of you could collaborate. I kind of sense that happening, possibly. And Jeff, I don't know if you know Nick. I don't know who you know.
Yeah, we know each other. Yeah.
Yep. Nick and got me into the board of directors.
Oh, super. I kind of sense that, but I don't want to assume anything. Okay. So
another question. Jeff's presentation was in terms of general relativity and comparing the natural philosophy or the integral calculus approach to general relativity. Now, special relativity is quite different, and I know that you were talking with Harry in terms of special relativity, but special relativity doesn't have, doesn't talk about curved space-time. But I do think what you were talking about does apply to special relativity, and I just wanted you to specifically talk about that point.
But and I do agree it does apply, but I guess in all the arguments I've seen of special relativity, and I have gone 180 degrees where I now have a good appreciation of what everybody else here is saying. I guess the issue I have with expending my time on special relativity is that I think that no matter what argument you come up with, and no matter what evidence you show to prove special relativity wrong, that people, yeah, if you've ever heard of Fourier and Laplace, Fourier came up with this equation where he showed that you could have the summation of all these certain terms and stuff uh, equaled something else. And Laplace was this amazing mathematician, and even though it was proven to him, he still didn't believe it. So I think that even if you proved special relativity was wrong, I don't think the mainstream would have any would end up turning around on it.
We still got to reach the next generation, and that's a whole
I
other
think
debate.
so. I think some people got to die.
Yeah,
So
you're right.
that's
Just one final comment. Harry was talking about how special relativity was wrong mathematically. But I think the error, and I think there may be some applicability here to Jeff's approach, was his problem really wasn't so much a math error as he didn't think through what the implications were for the physical model, and the physical model didn't make sense.
right.
So that's my final comment.
I agree. And if your basis is on mathematics and you come up with this perfect mathematical model and it's beautiful, you may not care whether it matches the real world or not.
Right,
So,
right.
that to me seems at the heart of special relativity is you have this beautiful mathematical model. It may not match the real world, but boy, it certainly seems to have a lot of applicability, at least at the parts that you only want to consider.
That's right.
I have more a question than really an answer, but something to think about. And that is, you just kind of pass this off casually, and in my mind, it's like an enormous question that needs to be solved. And that is the question of, does an absolute frame exist? And I think most of the people here would say yes. And I don't want to, how do I say this in a way that doesn't get a lot of offensive because I'm not agreeing with Einstein, and yet I'm still, and I don't want to have a bunch of real quick answers because I believe that energy should be energy that you measure is not a function of a point of view. Energy is a matter of relative changes of actual physical objects. So, and this I struggled with a great deal, a lot. I mean, like years and years and years. So don't pass it off quickly. What I mean is that if you're just going to change reference frames and now then suddenly your mv squared is a different number, okay, then your energy is a function of your point of view. And there's something wrong with that whole approach. That whole approach is wrong. We've got to start over and say, no, wait a minute. The real energy does not depend on how somebody is observing it. It depends on how one thing is moving relative to some other thing. And the combination of those things is what creates the frame for that point of view. So the absolute frame, which does exist at a given point, is not necessarily the absolute frame that exists at some other point. And so what is the absolute frame? Wow, I don't know. And does one exist? I don't say no, and I don't say yes. I say that's a really difficult thing. Anyway, that's my 2 cents as far as what you said. Your casual remark on you can prove that there is an absolute frame. I didn't even know which absolute frame you meant, because I interpret an absolute frame for a given point, which can be different from the absolute frame at some other point, is not the same as an absolute frame. Anyway, so again, if you don't have to say anything, I'm just throwing that out. If you want to comment on it, go ahead.
That was very confusing, Greg.
I think I do have a little bit of a concept of what you mean. To me, when I think all absolute frames are equivalent, I always think back to the experiment that if you're traveling in a spaceship and you don't have any view of the outside world, that according to relativity, there's no experiment you can do which will tell you that you are moving if you are at a constant velocity. You can't tell whether that, and to me, that as far as I understand, is the one of the experimental definition or physical definition of relativity.
That's
And
Galilean relativity.
that's Galilean relativity.
Yes.
I was under the impression that that was, well, all right. But my understanding is what I'm trying to do is ask a very simple question and build all the way back up to those to try to get a fundamental understanding of when we say something is energy, how do we define it? And whereas I view the geometry does have a lot of explanatory power, but it also can explain things, why things are wrong with the way that we look at relativity now. You know, how is it that I can end up with a singularity in space-time coordinates? How
Yeah.
is, how is that even physically possible, or even conceptually possible? How is it that I can have another type of energy? I have my regular energy, is what we're talking about, but supposedly that's less than 4% of the universe, and that most of it is this vacuum energy density, which is modeled after a cosmological
Yeah.
constant.
Can
You
I
know,
interrupt you a little bit?
sure.
The problem is for physics, we're talking about physics. Okay, my view is this. If you're talking about physics, and as soon as you say the word physics, you have to talk about measuring something.
Hmm.
Okay?
Right.
The difference between physics and philosophy is that what you're measuring in physics is something that exists in the real world, supposedly. And so that's what differentiates physics from geometry and mathematics and philosophy, because there you're not talking about things that are real, they're imaginary. So talk about measuring things, okay?
Right. Oh, okay. Well, I mean, the way I view it is that when we measure things and we see that things don't work exactly like Newtonian physics tell us in the small part, and even in the larger part, we see very big changes. Is that to me, it's like, well, what we're measuring is actually an approximation of something else, and that if you know the old analogy where you feel around an elephant, but you're blindfolded, and everybody feels a different elephant or a different animal, but you're actually all feeling the same one. You just have different ways of describing your little area that you're feeling. So I view the same thing as with a measurement, that you're actually viewing something else, and whereas somebody else takes a measurement, they're viewing a different angle of it and everything. But that there is a simpler underlying theory or a simpler underlying language. Doesn't mean there necessarily has to be, but that's what I am searching for. Is there a simpler underlying way that we can explain the rest of this?
Okay. We're at 10:30, and there's still more time if you want to devote some time to it. And if not, if anybody has more questions, we can certainly ask them. Um, our group got smaller. Some people left, but the core is still here. So yeah, unless there are further questions from anybody in particular, why don't you go ahead and give us a summary, Jeff, of what you think you can accomplish with this work, and where you think it might go for your own work, and maybe addressing Nick's question, what you think, how you think this approach might be something that could be used with the mainstream.
Okay, so what this approach is that I am taking a basic assumption about these perpendicular line segments. And what I'm hoping to do with geometers in the mainstream is to say, take a look at these properties of these relative line segments, and take a look at the properties of what you're calling of a metric and how this metric changes. And all of these things that have been derived, all of these properties that you derive from changing this metric or leaving it constant, also seems to have what I'm showing. It has to seem to have the same properties of this relative area of these perpendicular line segments, and that the phenomena that you predict from changing this metric seems to have a correlation as if I change this relative area. And so whenever they bring in what these argumental devices where they bring in this perfect fluid and everything else to combine with this metric to describe how energy changes space and time, seems I can also say that I have a similar analogy using this relative line segments here. And that is the whole goal of this, is to show there's a different way to look at geometry, and that perhaps that some of the answers that this provides shows, and compare those to how general relativity does it with this metric concept, that we're actually looking at the exact kind of the same thing. Maybe we can answer some of these questions. But the problem is that the farther I go with my research, the more natural philosophy looks correct as a correct viewpoint of the way to look at the world. So that's the downside to this, is that it pulls me away from the mainstream, because it kind of, the more I look at it, it kind of disputes what we're doing in general relativity. Even if geometrically I'm saying they're very similar, it doesn't agree philosophically with how it was done in general relativity. And and just to add on a little bit at what I was talking about, so in when we do the July conference, I'm going to be bringing a description of a physical experiment that I'm proposing, that I'm going to be trying to get done. And what this physical experiment was, this is what really got me started on it, is that there is something, I believe, about ether wave theory that can solve an old physical paradox, which mainstream physics cannot. It's a question in mainstream physics, but ether wave theory can answer this. So I'm going to propose how this would do it, and I will explain step by step on why I believe it would help out. And hopefully, maybe that would give an impetus to bring natural philosophy more back towards the mainstream, and that it can provide answers that mainstream physics can't. So that's hopefully something I can present in July.
Super. All right. Is there anybody who wants to make a comment before we go?
Yeah,
Or
yes, I'd like to make a comment. There's a paper by Ronald R. Hatch, 2007,
Ron Hatch.
physics essay, and it's called The New Theory of Gravity.
Danny, just so you know, we're getting feedback from you, and it might be helpful to get a headset in the future.
Okay, I'm sorry, I don't have a headset. Anyway, this paper is about 30 pages long, and it shows that, starts out by showing the general relativity is wrong because the equivalence principle is wrong. Then it goes on to show that special relativity is wrong because the GPS system was run as one of the chief architects of wouldn't work properly if special relativity worked correct. But it does work.
Okay. So this is a Ron Hatch paper from 2008 that you're recommending.
2007.
2007.
Physics essay.
And it should be on the website, physics essays, which are not all necessarily downloadable, but I have a lot of them. And Ron would have them if you can't. If you want to contact Ron yourself.
Okay.
Okay. Thank you, Denny. I'm going to mute you because we are getting feedback from you. All right. Julie Haberly just came. Hi, Julie. You're just in time for us to quit the meeting. I think I'm getting feedback from you too, Julie. I'm going to mute you if you don't mind.
You have to mute Mitch Haas.
Is that what it is? Okay. Mitch,
It's
sorry.
always someone else.
But Mitch doesn't even have mute is not an option in Mitch's case.
I saw it now, Mitch Haas. There was a little.
Oh, there we go. I just did mute him. All right. Oh, maybe we're. Well,
now it's on music.
Okay, whatever it was. Okay, that wasn't you, Denny. I'm sorry. It was somebody else, but that's okay. All right. Well, and Jeff has already given us some closing remarks. So, Julie, I'm sorry. You just got here at the tail end. We were just about ready to quit, to call it a quit. I'm still learning the system, and thank you for everybody for your patience and trying to figure out the system. Hopefully we'll have some more of these in the near future. It really comes down to just, getting some people to come and speak and present. If we get that, we can get the group going again. So, I appreciate everybody's time and look forward to this July for the new conference. I'm going to close out the recording. I hope I can do it. And thank you all for coming. Here we go.